Log on, tune in, find out. Another good idea from Cambridge.
Ready, so they can collect it in the reception. And we will start with this lecture that Valery will talk about the introduction of moduli varieties.
Moduli varieties. All right, so I'm still not sure at what level I should pitch these lectures. The organizers strongly insisted that we should be pedagogical and stay elementary, but then it feels like I would lose face, you know, if I'm too elementary, because other lectures are, some of them are quite advanced. Anyhow, I decided to take it to heart and stay elementary. And certainly today's lecture is aimed at beginners. And then Tuesday, Wednesday, Thursday, those lectures will be quite combinatorial. So it doesn't matter if you're a beginner or advanced. It matters more if you like combinatorics or if you can, at least you can absorb it, even if you don't like it. And then Friday could be a little more advanced, okay? So no apologies for the last lecture. So this is the plan for today. This is what I'm going to talk about. And let me start with this general question, you know, what is a moduli space? And there are many answers to that question. There is a naive definition, so maybe I'll call that a naive moduli space. And then there is something that's called fine moduli space. And then there is a coarse moduli space. And then there is something that I will call a weak moduli space, but maybe someone knows a better name, so tell me. So I think most people just call it just a moduli space without any further adjectives. So what are those things? So let's start from the beginning, even if even for the naive definition, let's fix the category that we are working in. So we will fix some base scheme, and so all the other schemes or varieties will be over this base. And the easiest is, say, maybe we just work over complex numbers, or maybe over rational numbers, so there is a little bit of arithmetics already. Or maybe we work over integers. You know, then we are really ambitious. And then we work with varieties or schemes over this base. And so what kind of varieties? For example, we work with all schemes over the base. So that's the most ambitious case. Or maybe we are scared a little bit of non-Noetherian schemes and we work with Noetherian schemes. Or sometimes, for some methods, people only work with schemes of finite type. So that's a good choice as well. All right, so we have that. And then we fix some class of varieties that we are going to parameterize, that we're going to construct a moduli space for. And so then there is this M, moduli space. So what is it? And for the naive answer, we just require that the points of M are in a bijection with isomorphism classes of varieties in this class. And already if we say that, then it's not completely trivial, because you ask, you know, what kinds of points? In algebraic geometry, one has scheme points, and one has S points. S here is a scheme itself. Or there are R points. R is a ring. Or there are geometric points. And geometric points are, well, this is the same as this is K points, and K is an algebraically closed field. And so this is the right answer. So in this statement, we talk about geometric points. And so if you have M, a variety, then you have this M over K. These are K points. These are solutions of M. M is an algebraic variety, say. So solutions in K. So M is given by some polynomial equations, so these are just solutions with where the coefficients are in K. And K, I remind you, is an algebraically closed field over your base. So if you work over Q, that means it's a field of characteristic 0. And if you're in this category, then then in addition it will be of finite type over Q. Well, closure of a number field, so just Q bar. Okay, so let's call this property number 1. So in the naive, for the naive moduli space, some people just say, when they see something like this, they say that's a moduli space. If you have a variety whose points are in a one-to-one correspondence with isomorphism classes, that's a moduli space. Of course, that is, if you just think just for a second about this, that's very unsatisfactory because for many reasons. One reason is that there are many varieties that have exactly the same points. Say a cuspidal curve and just a line, there is the same. There is a map like this, and it's a bijection. It's even a homeomorphism of topological spaces, so they're really not different as point sets. Or maybe you can add a nilpotent, and then you haven't changed the points. Still, among all these choices, sometimes you can pick the best one. Let's say your moduli space is smooth, then you cannot really improve on that. So you say that's the moduli space. A deeper reason why this is not good is that if you just say points, then as a set, it only has cardinality and nothing else. And so somehow our statements should include algebraic data or algebraic structure. And so one has to talk about families. So for moduli spaces, it's never about just isomorphism classes. It's about families. So then people define the moduli functor. So moduli functor and moduli stack. And I'm running out of letters, so maybe tilde or something for the moduli stack. And so a moduli functor is a functor. It's from sets, from schemes, which is sets, and it's a contravariant functor. And so this M of S is a set. And for the moduli stack, so you have lectures on moduli stacks, so you know everything about them. So this is a category instead of a set. And so what we have here, we have all the good families of your varieties, moduli and isomorphism. So this is isomorphism over S. So So that's you. To every scheme S, you associate this M of S. And good, so what is good? For many problems, good is just flat. We know that, but not always. So there are many examples where good is really something stronger than flat. It's flat with some additional conditions, and I'll give examples of that. All right. So then, so what do we have here? So we have S, and we have some family. And this is the family X, and this is pi. And then here's our moduli space. And if you have a point in S, then there is this fiber. Fiber is one of your varieties. And in your moduli space, there is a point which corresponds to that isomorphism class. And so therefore, you can map this point to that point. And you just map the point S to the isomorphism class of the fiber. And then the other point you can map somewhere else. And then the whole base you can map somewhere. So what you get then, you started with this family, and you produced a map from S to M. And of course, the condition now, the algebraic condition, is that this has to be an honest morphism. So a morphism of varieties or a morphism of schemes. So now it's no longer about cardinalities only. And what is this? This is an element in here. This is a good family. So this is an element in M of S. And what is this? This is an element of this functor. These are just morphisms from S to M. And so that's what we have then. And and then you do it for all S. For all bases S, and it has to be all compatible and nice and functorial. So therefore, you get a phi. It's a natural transformation. It's a morphism of functors from your functor M to this functor morphisms to M. Okay? So that's that will be our condition 2. That's the standard condition 2, that there exists this phi, a morphism of functors from M to morphism to the moduli space M. And then the third nice condition one can consider is phi should be universal. And this means that if you have some other phi prime, these are morphisms to some other M prime, then there should exist a unique morphism here making everything commutative. So that's a universality property. So in the naive, let's state that condition 1 a little better in this language. So this condition just says that for every algebraically closed field, M of k is M of k. So these are just isomorphism classes of varieties over k, and these are k points of M of your solution. So in the naive definition, it's just the condition 1. And it's still okay in some cases, so even though it's so deficient. For a fine moduli space, this is the standard definition, you require 2 plus. And 2 plus means there is that phi, and moreover, phi is an isomorphism. And so an isomorphism.
2 is related to 1, yeah?
And 2.
Points is something?
Such that, right. So there is this morphism, right, such that for S equals spec of K, this is this gives the correspondence in 1. So this gives 1. Thank you. So for the fine moduli space, you have 1 and 2 plus. And 2 plus says that phi is just an isomorphism. And in other words, there is not just the moduli space, M, but over this moduli space, you have a universal family. This universal family has to correspond to some morphism. And it's the morphism from M to M. And it's just the identity morphism. So in this functorial language, if phi is an isomorphism, then the families are precisely the same as morphisms to the moduli space. And so identity corresponds to some family. And this is the universal family.
Something
Yeah.
You might make your family globally twisted and get the same phi. So you don't want this to be an isomorphism.
No, I really do. So for the fine moduli space, there are no automorphisms, which you can easily prove. So for the fine moduli space, one easy implication of fine moduli space is that every variety in your class has a trivial automorphism group. And there is this universal family, and then any other family is obtained by base change. So you just take your S, you map it somewhere, and you just pull back. And this family X universal times S over M is, you get all the good families in this way. So that's fine moduli space. In the coarse moduli space, it's 1, 2, 3. The conditions 1, 2, 3. And in the weak moduli space, it's just 2 really. So it's 2. So if you just look at what 2 is, let's put 1 and 2. Okay, I don't want to use 2, so I just want to use 2 and 3. No, please don't contradict me. So what I'm trying to say here is that if you have something that's defined by universality, so some scheme defined by universality, then this universality immediately implies that it's unique, that your object is unique. Just anything defined by universality is unique. And so sometimes you don't even need 1, or you can get by with something weaker than 1. And so moduli of vector bundles of semis.
For fine moduli space, 3 is 3 not.
1, 2. Well, that implies 3. So let's just put it here. But if it's but 3 is implied by this very strong condition. So an example of a weak moduli space is the moduli space, very familiar to most of you, just moduli space of vector bundles, of semi-stable vector bundles, modular GR equivalence. And then, so this GR equivalence, you can give a definition without GR equivalence, but by losing the first condition. All right, so I only have so much time, so let's move on to the second part. And that would be examples of moduli spaces. The very first example, and the nicest, is Hilbert schemes. And then one has Chow varieties, and so MG or MG bar or MGN bar, and for modular F surfaces of general type. And stable surfaces. Of general type. So let me briefly discuss all of this. So the Hilbert schemes, that's the absolute prototype for most moduli spaces of varieties. And the objects here, so the class C that we consider, is the following. So we fix some projective space, and we look at Z in Pn, a closed subscheme. Let me call it X. Subscheme. And then we have to say what is a nice family. So a nice family would be some closed subscheme here, which is flat. Which is flat over the base. So that's a nice family of closed subschemes. Now, if you say flat, then you restrict. This means you restrict to Noetherian schemes. But the way Grothendieck did it, he did it in a more general situation for all base schemes. And then you replace this flat by some condition that, let's say what the condition is. So if you have a family like this, then you have the structure sheaf of Pn cross S, and it surjects to OX. And so these are OS modules. So if you are not satisfied with flat, then you require that this one is locally free. And then locally free implies flatness, but it's a stronger condition, and so can be worked in a more general situation. For maybe I have to say the standard thing. Mention this standard fact that if you have a closed subscheme of Pn, then you have a Hilbert polynomial. And the Hilbert polynomial is P of n, Px of n. It's the chi characteristic of Ox twisted by n. And in flat families, the Hilbert polynomial is constant. So it makes sense just to fix one of these Hilbert polynomials. And then the statement is, due to Grothendieck, that there exists, for this moduli problem, there exists a solution. And it depends on Pn and this polynomial P of n. And I'll say a couple of words about later on about how to construct it. Now, for the Chow varieties, again, you start with the projective space and you fix a dimension d, a dimension m, and a degree d, and then you look at z in Pn as cycle. So a cycle is just a formal linear combination of irreducible subvarieties, and they all have to be of dimension m. And the degree of this cycle has to be m. And then you want to say what is a family of cycles. And a family of cycles is just a cycle on Pn cross S. So the Chow variety historically appeared much earlier than Hilbert's scheme, but it's a much worse moduli space. And one reason is that this family of cycles is not a very nice thing. To begin with, if you take S to be just a point, or you take S to be a point with a nilpotent, then a projective space over a point, or a projective space over a point with a nilpotent, sort of a thick projective, a little thickening. These are exactly the same topological spaces, and so the cycles are exactly the same. And so there is no difference between cycles here and cycles there. And so therefore families just don't see nilpotents at all. That's one thing, but it's more than that. Cycles don't see singularities like cusps. Families of cycles over a line are exactly the same as families of cycles over cusps. So they don't even distinguish such things. And so there is a definite problem. And so we can say that Hilbert scheme is a rich moduli space. We can look at all bases as arbitrary schemes, don't even have to be Noetherian. And Chow varieties is a poor man's moduli space. And so your basis, you can just restrict to reduced semi-normal basis. And then you have you have this moduli problem, and it has a solution due to Chow and really due to van der Waarden, right? Chow was a student of van der Waarden. But, okay. Now, for MG, of course, your class of varieties are just smooth projective curves of genus G. And for MG bar, these are stable curves. I'm sure most of you are familiar with that. Let's say what they are anyway. Let's see if we agree on such elementary definitions. So what is a stable curve? So a stable curve X is a reduced, projective, connected curve with nodes at worst. And the dualizing sheaf has to be ample. So that's my definition of a stable curve. And so for most people, I think the definition is that it's a curve like that and has to have a finite automorphism group. And, but that's equivalent to this condition. The degree of this dualizing sheaf, if you restrict to a single component E, then it will be twice the arithmetic genus of E minus 2 plus the number of points in the intersection. And
If you fix some points in a curve, you will have to modify the definition.
say again, if you fix that?
If you fix some points in a curve,
Right,
you will
right,
have
right.
to modify the definition.
Yeah, so let's do that. Well, let me use a
But
different.
when you use a normal definition, you don't have to modify it.
But if you use weights, then your definition doesn't work and my definition works. So if you, let's do this modification first. So for mg and bar like this, you also fix endpoints. So the order is important, so you really call them P1 through Pn. And then here, instead of omega x, you look at omega x sum of pi. Omega x of sum of pi. And so the condition is that omega x of sum of pi, this should be an ample sheaf. And so the only difference will be here I have to count the points which lie on this particular component. This has to be positive. Again, this is just equivalent to saying that the automorphism group of a pair is finite. There is none of them is stronger. They're equivalent. But then there is the version that I will talk about on one of these days. And here, in addition to n, you fix some weights. So b1 through bn. And these weights bi are between 0 and 1. And then you can ask for this condition. And here you count them. You count the weights. Over these points. So that's a weighted Hash's weighted stable curves. And then this condition is stronger than the condition on the automorphisms. All right, so for surfaces of general type, that's 4. Surfaces of general type, you can start with smooth surfaces of general type. Then, for surfaces, there's birational geometry then now. And if you start with a surface of general type, you blow up many points. That's still a surface of general type. So really, one talks about this. It's one assumes more, and it assumes that the canonical class is ample. So the dualizing sheaf is ample. So it's general type plus, if you like. Well, the surfaces are smooth, but these moduli spaces are already extremely pathological, and they can have arbitrary singularities. They can be non-equidimensional, et cetera, et cetera. So there are these phenomena of pathologies of moduli spaces. That's one of those moduli spaces where everything bad that can happen happens, even though the objects are nice. And in number 5, so stable. Stable will mean it has some kind of nice singularities, and the dualizing sheaf is still, I'll just write kx example. But all of this has to be clarified. Okay, so with this little list of examples, what did we have for 3? 3, the good properties. And they are polarization. And even better if it's canonical. And second part is boundedness. And the third part is finite automorphism groups. And an extremely important condition is local closedness. So what's that thing? So it was understood a very long time ago that it's if you work with some polarized varieties, not just a variety, but a polarization, which is an ample line bundle, then you can expect some nice moduli spaces. And if you work with varieties without polarization, then typically you get something horrible. And for example, for surfaces, for abelian varieties or K3 surfaces, if you look at the moduli space without polarization, just the isomorphism classes, then it's a horrible mess, this moduli space. But if you work with polarized abelian varieties or polarized K3 surfaces, then you have a nice moduli space, which is a quotient of a symmetric domain, etc. Now, boundedness
Sorry, that's the property of the moduli space, or is it object?
of moduli functor, I said, right? So it says a moduli functor. So we define the moduli functor, and it's a nice families. And so it's families of what? So it's always better if you work with polarized families with some ample line bundle. And a canonical polarization is if this polarization is really intrinsic. It's not external. It came from the variety itself. So surfaces of general type, if we assume the dualizing sheaf is ample, then that's our canonical polarization. And for n-pointed curves, our canonical polarization is this omega x of sum of pj. It's just this ample line bundle. So it's polarized, but intrinsically, we didn't have to. It was already part of the definition. So for boundedness,
That's not really a property of the moduli functor.
should I say it's property of what? Of our class, of a moduli problem, of a moduli.
There's no abstract phrasing of this kind of.
Right. It's a property of a moduli question, right? So the question is, what's a moduli space for these objects? And so it's better if the objects are polarized. Now, boundedness, you would use this polarization. And so for boundedness, you would ask that there exists some n such that L to the n is variant. There is some fixed n for your varieties that gives you an embedding into your projective space. And of course, it's good because then you have your Hilbert scheme. And then you can start from that. So you can somehow cut down from or divide by some equivalence relations from the Hilbert scheme. But that's in most problems it's really obvious. For smooth projective curves of genus G, well, we know that 2K or 3K is very ample, and so you have a fixed embedding. Well, you have embedding into a fixed projective space. So you have your Hilbert scheme. Finite automorphism groups, okay, that's self-explanatory. That's for the methods I'm going to talk about, that is very necessary to have. The methods just don't work without this condition. Now, finite, in characteristic P, your automorphism group could have nilpotents. Still, it should be a finite group scheme. And local closedness means, well, suppose you have just an arbitrary family. Let me say, not such a nice family. And you want to, T maybe, and you want to somehow carve out of this general family your nice family. And then, so you have S, and if you have a morphism from S to T, then you have your fiber product, X times S over T, so just the pullback. So this is S, this is the pullback. And you ask, when is this a good family in your definition? And then the requirement in this condition is that there exists ST, what are good letters? Doesn't matter, let's say P. P and it's locally closed subscheme. So disjoint union of some PI. And so your pullback is nice if and only if this map factors through this locally closed subscheme. So there is some subscheme that sort of maximal subscheme over which this family is nice. And but that's how you would say functorially. So the pullback is nice if and only if you map exactly to P, or you map through P. Okay. Standard. I'm missing a number here. And the number that I'm missing is very important, and it's standard methods for constructing moduli spaces. And there are basically 4 methods by hand. That's a very important method. And then there is GIT. And then there is Artin's method. And then number 4, quotient by flat equivalence relation. And applying Hill-Mori. So the first and the most well-known application of the first method is that's the Hilbert scheme. So if you have a variety X in Pn, then you have an ideal in your ring of polynomials. Then there is a quotient. And vice versa, if you have a graded, a homogeneous ideal in this graded ring, then you have a subscheme in the projective space. And then a little trouble is that different ideals may give you the same closed subschemes. It only matters what these ideals are in large enough degrees. So that's the main complication here. But ignoring that, what you want to investigate here is that if you have this homogeneous ideal, then for every degree, you have a vector subspace in this vector space. And so then the question is, which collections of vector spaces correspond to ideals? And can you define this closed subscheme by just specifying one degree, one large enough degree? And so these are some algebraic questions that you can define and solve. And I certainly don't have time to talk more about this, but that's really essentially, so you reduce this general question to a question about Grassmannians plus some polynomial conditions on these Grassmannians which correspond to ideals with a fixed Hilbert polynomial. GIT is a study of quotients. You have lectures on GIT here, so I don't have to talk more about it. It gives one thing about nice thing about GIT is that it gives a projective moduli space. The GIT quotients by very definition are projective. Now, in the Artin's methods, you study deformations first. And again, I believe there are lectures here on deformations. And this is the hardest methods of all of this. So you really have to carefully study deformations of your varieties and infinitesimal extensions, and some Artin's conditions have to be satisfied, and then there is then you algebraize and approximate by an algebraic space. So this is the most sophisticated of all. And then the fourth method is the easiest for applications.
You mean flat groupoids, right? Because flat translation is a simple enough.
In which part? In four.
Flat groupoid rather than
Right.
than translation.
Mm-hmm. Yeah. So let me. This method is the easiest for applications. It's really a machine in which you can plug in a few ingredients, and it spits out a moduli space. And so in this case, you have some U, let's say scheme, and you have R times U cross U, a groupoid or a groupoid equivalence relation, and you want to construct a quotient. And then, so for as long as you know that J is flat, then there is this paper of Kiel and Mori, flat and so flat equivalence relation, and with finite. Then this Kiel and Mori paper says that there exists a geometric quotient, which is also a categorical quotient.
They don't need finite. Finite was already in SGA3.
Their theorem is stronger, so their condition is that the diagonal is finite, and then there exists. That's the conclusion. But if J itself is finite, then this is also separated. That's that.
What is the groupoid equivalence?
Mm-hmm. So instead of saying that, why don't I give a very quick example of MG? So groupoid just means it has properties satisfies the group axioms. That's what the word groupoid is for. But it's just an equivalence relation. Let's run this quickly through MG bar. Let's just run it through MG, okay? It's an easy moduli problem. By hands, we already have a Hilbert scheme. So if we fix G, then we know that every curve of genus G can be pluricanonically embedded into a projective space, which whose dimension you can compute, and whose degree you can compute, and whose Hilbert polynomial you can compute. Well, let's compute it. So it's 2g minus 2 times k for the degree, and then there is 1 minus g. So that's the Riemann-Roch computation. So that's the degree. This one. So you already have the Hilbert scheme, and over this Hilbert scheme you have a universal family of subschemes with this Hilbert polynomial, and then you apply the nice property of your moduli space, and the nice properties here are that, first of all, these schemes can be horrible and singular, but you only want to look at non-singular curves, and so that's an open condition. That's nice. But then the curves embedded here, they are not necessarily embedded by O of KKX, by a pluricanonical line bundle. Instead, they are just embedded by some ample line bundle which has the same degree. And so what you want, however, you want your polarization to be exactly that. And that's a closed condition. And so as a combination of that open and closed, you have locally closed. So you have now some H, which parameterizes pluricanonically embedded curves but embedded curves. And you want to get rid of this embedding. And if you use GIT, then you want to find the quotient. This quotient. And then you have to solve this GIT problem. So you have to prove that smooth curves, pluricanonically embedded, are stable or semi-stable. And that's a very hard problem. So for curves, that was solved by Mumford a long time ago. For stable curves, the usual argument is indirect. So it was traditionally, it was not proved. It's such a simple problem. So of course, by Mumford, these pluricanonically stable curves are semi-stable for as soon as k is at least 5. But if you want to prove that they are stable, then the standard argument is roundabout, is indirect. And finally, last year or so, Jun Lee and his co-author Wang proved it finally, that stable curves are stable for GIT. So that's curves. And then in higher dimensions, you can see this is a very hard method to apply because it's very hard to prove semi-stability and stability in the GIT sense. In this, if you, however, use this relation, then what you have now, you have an equivalence relation, and here's your equivalence relation. It's just PGLN plus 1 times h mapping to h cos h. So this is R. And so G and X map to X and GX. So that's the equivalence relation by which you want to divide. And it's an equivalence relation you can reformulate it by, in this language of groupoids. But it's so it's a flat map, and it's finite. That reduces, in this case, to the statement that the automorphism groups are finite. And then, so by this machine, then it's immediately, you have this moduli space, in one step. And however, this moduli space, unlike GIT, this gives an algebraic space instead of an honest scheme. So if you want to prove that it's a scheme, then there is more work. But if you're satisfied with an algebraic space, then you're done. And so that's very easy to use in higher dimensions. Now,
Can you construct and using GIT or this quotient by applying flat equivalence relations?
say again. So you can
Do you
use.
get the same moduli space?
Yeah, it has to be the same just by the universality, right? By the third property. So it's a coarse moduli space. I have to say that. Your result is a coarse moduli space. And coarse moduli space had that universal property number 3. So it's unique if it exists.
Yeah, but did you know that a priori? You said it was an algebraic space.
Right, this method only tells you that it's an algebraic space.
So you don't a priori know that you get this.
Not if you use this, right? But if you use GIT, then you know. And then Arkin method, so Arkin proved, reproved this statement using his method and using deformations of curves. So that can be done as well. Now, I still have a few things, right, for 5 and 6. What did I want to say about 5?
J composed with the projection J flat. J is not flat. J composed with the projection is flat.
Right. So
Just like J flat and J composed with projection.
So J finite, J composed with the projection. Thank you. And so, just because PGLN plus 1 is flat. So number 5. Let me speed up a little bit, and I will just formulate the end of it, and it's a meta theorem. And here's what this meta theorem says. that there is a very general setup, which is kind of universal. And for varieties or pairs in this setup, there is a nice moduli space generalizing mg bar and mgn bar. And so there is a nice moduli space for stable pairs. And stable pairs, these are pairs xd, xb, where this is a projective variety. These are divisors. These are coefficients between 0 and 1. And stable here, there are so many definitions of stable in algebraic geometry. Right? There's this Pankhari-Pandey-Thomas stable. That's not it. So this stable means that this pair has SLC singularities and that kx plus b is ample. So it's stable in this sense. And SLC means semi-log canonical. And because I'm out of time today, then I will have to explain it next time, what that means. But let me say that in this example, stable curves have SLC singularities. So these are the simplest singularities in dimension 1. They're nodal. And kx plus b have to be ample. Well, there was that condition. Now, where this comes from a very simple observation, and it's the one, again, I will have to explain next time. But if you look at the degeneration of curves, and if you try to construct a sort of a canonical limit, some nice limit, the answer is that the nice limit is a stable curve. But how do you find that? And so you find it first by first applying the stable reduction theorem, which gives you some limit which is reduced. So nodal and reduced. You get this limit after a finite base change, maybe. And this limit is not unique because you can, this is a surface now. So on a surface, you can blow up a curve, blow up a point, and insert a -1 curve, and there will be another limit. So if you want some kind of canonical limit, then you contract, you start with a limit, some limit like this, and then you contract -1 curves. And while you're at it, you also contract -2 curves in the central fiber. And so that limit is unique now. That limit, after contracting -1 curves and -2 curves, is a stable curve in the sense of Deligne-Mumford. But what this is the simplest example of birational geometry for surfaces. And what you just did when you contracted -1 curves and -2 curves, here you found the minimal model. And after contracting -2 curves, you found the canonical model. So you just ran the MMP, the minimal model program, in the simplest situation. But now, we all heard about these powerful examples that have been proven several years ago. So we have minimal model program in all dimensions. And of course, in dimension 3, we had it for a while, for 15 years. So you can do the same procedure for families of surfaces, etc., for families of threefolds. And you will find these canonical limits that MMP provides you. And they have some singularities. And that's what SLC singularities are. SLC singularities are, it's whatever you get in this construction. That's what SLC singularities. And all right, so I'll just say number 6. So Tuesday, Wednesday, and Thursday will be free lunch. And what this is, and then Friday will be honest work. So if there is this meta theorem, and so there is this general scheme of doing things, you can try to do it for surfaces, and you run into many problems, many complications. I will discuss those on Friday. It's hard, honest work. But then there are several situations where you almost don't have to do any work, or you have to do something else, and then for free you get this modular space. So for example, for toric varieties, toric varieties are very simple, very easy. It turns out they have they have log canonical singularities. I mean, who would expect, but they do. Or another situation is degenerations of abelian varieties. Again, you can construct this compactification somehow without using MMP, but the answer is what this meta theorem suggests it should be. Or for hyperplane arrangement, there is a construction of the moduli space which doesn't use any MMP, hardly uses anything. It's just some linear algebra, in the sense that anything about Grassmannians is linear algebra. So it's just some Grassmannians, and then somehow the answer is a nice moduli space of nice SLC stable pairs. Now, if you try to do, so that's what I will do on Tuesday. I'll do stable toric varieties and the degenerations of abelian varieties. Then on the day after that, hyperplane arrangements, and then on Thursday I will show you many examples of moduli of surfaces of general type, compact moduli, but there are sort of free lunch. So I mean they're accidental examples, so to say. And then on Friday I'll try to go into those hard problems. Let me end here.